very good morning and welcome to this course on the foundations of continuum mechanics. This week we start with our discussion on balance laws, and for that we will be talking about the transport theorem, also known as the Reynolds transport theorem today, followed by the discussion on conservation of mass or the continuity equation. So let us get started with this lecture. So the topics for today's lecture will be as follows. We will first introduce balance laws to you. Then we will derive the transport theorem, which is also known as the Reynolds transport theorem, and it is one of the most important theorems which is used for the derivation of balance laws. And then we'll put this theorem into practice by studying mass balance, or also known as the equation of continuity. We will write this equation for mass balance both in the Eulerian as well as the Lagrangian forms. So let's get going. In mechanics, we need some equations to start with. And these equations are the equations which are based on laws of physics. So when we talk about balance, we talk about balance of mass or the conservation of mass. We talk about the momentum equation that is based on the Newton's second law, that is forces. And thirdly, we talk about the equations of energy balance, also known as energy equation. In the case of energy balance or the conservation of energy, we have to get into the laws of thermodynamics because heat transfer also becomes important. So once we have the balance equations to get started with, then we try to relate motion, that is the different tensors we have discussed in kinematics, with the quantities such as stresses, density, and so on. And finally, once we have an equation that we can solve for the different quantities related to motion, we can solve for the motion of the body resulting due to different forces, etc. So now we'll discuss a derivation of the transport theorem, also known as the Reynolds transport theorem, which is usually the starting point when discussing balance laws. So this theorem basically is providing us an expression for the material derivative of integrals which help us write conservation laws. So let us say we have a quantity denoted by this nth order tensor, that's Pij dot dot dot, which is a function of time. We can write this quantity as an integral over all the material points in the volume omega for the corresponding quantity P star, which is a function of small x and t. So P star is a local quantity times d omega. So this quantity P, which is a function of time, is called an extensive property. And extensive properties are properties which are contained in a collection of material particles together at some time t. So an example for extensive property could be mass. So if you have a lot of material particles, then collectively their total mass is an extensive property. Similarly, we could talk about momentum or linear momentum, which is again an extensive property because it depends on the total mass of the particles you're taking. So extensive properties depend on the amount or the mass of the material. And this corresponding quantity P star, which is also a tensor of the same order as P, but it depends on the spatial coordinates as well. So this tells us that this quantity is not dependent on the amount of material because it is defined for each spatial point small x, and therefore it is called an intensive property. So intensive properties are properties which are defined per unit volume or per unit mass. In this case, we're talking about property per unit volume because dimensionally speaking, we have P star multiplied by this infinitesimal volume, and that is equal to the extensive property P. So as a summary, for a collection of material particles, their total extensive property will be P as a function of time, because the property can definitely change with time. But for any given time t, the property is capital P, and we can write this as a sum of the intensive property times the mass or the volume for all the collection of particles. So for this present analysis, we're talking about P star being a property per unit volume. Later, we'll talk about properties per unit mass as well. But in a sense, they mean the same idea, that intensive properties do not depend on the amount of material. So if you're talking about mass as the extensive property, then the corresponding intensive property would be mass per unit volume in this case, so that will become a density. Similarly, if you're talking about linear momentum as the extensive property, then the corresponding P star in this case would be linear momentum per unit volume, that is the density times the velocity field. And as I said, in the transport theorem, we're interested in the time rate change of this property P. So we take a material derivative of Pij dot 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 as a function of time. So this gives us d by dt of the extensive property is equal to the material derivative of the integral P star, again it's a tensor of the same order, as a function of small x and t times d omega. So mathematically speaking, I would want to move this time derivative inside the integral, but I cannot do it right now because my integral is over omega, and omega also changes with time because omega is the configuration of the body at some time t. So as time changes, my omega also changes with time. So the neat trick I can apply here is that I can write everything inside the integral in its Lagrangian representation. And we know that if you're talking about the reference configuration, then the reference configuration is not dependent on time. So what I do now is I write my P star, which is a function of small x, but I write my small x as a function of capital X and t based on the mapping that we have. And since we'll be writing things as a function of capital X's, that is the Lagrangian description of the quantity P star, we will write our d omega in terms of d omega naught, where omega naught is the volume that the particles formed in the reference configuration. So if this is the collection of particles in the reference configuration, then at time t, they form a volume in the current configuration. So this is our omega at the time t, and this is the omega at t equal to 0, which we call omega naught. So an infinitesimal volume in the current configuration is denoted by d omega, and an infinitesimal volume in the reference configuration is given as d omega naught. So I'll write my d omega in terms of d omega naught, and I showed in the previous lecture that d omega is written as the Jacobian times d omega naught. And now that things are written in the reference configuration, the summation or the integral happens over omega naught. So you must understand that it's the same particles that we're considering, but instead I write my P star for all those particles in the reference configuration using the Lagrangian description and multiply by their infinitesimal volumes in the reference configuration. Now in this function P star, if I write my small x in terms of capital X and t, then this function takes a different form, which I will write P tilde as a function of capital X and t. So the value will be the same, but the function, the mathematical function we will get will be different. So in our discussions, we'll be using the tilde symbol for the Lagrangian description and the non-tilde symbol for the Eulerian description. So now that this integral here is written over omega naught, so we can move the material derivative inside the integral, because this integral or a sum is happening over elements which are not a function of time. So basically our d omega naught is not a function of time. So the d by dt of the extensive quantity Pij dot 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 as a function of time becomes integral over omega naught d by dt of P star tilde. Again, there's an ij dot 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 here as well, which is a function of capital X and t times the Jacobian j times d omega naught. And here I can apply the product rule. So this becomes d by dt of P tilde star. I won't write capital X and t just for saving some space, but since it's a P tilde, so it's understood that it's a function of capital X, that is, it's a Lagrangian description of the quantity, times j plus P tilde star times d by dt of the Jacobian j. And we'll use the notation as earlier that the material derivative will be denoted with a dot on the top. So that makes it more compact to write it. It's a P tilde star with a dot on top times j plus P tilde star times j dot multiplied by d omega naught. And again, from the discussion in the previous lecture, we saw that j dot can be written as divergence of velocity times the Jacobian. So this simplifies further to P tilde dot plus P tilde times the divergence of velocity, which in the initial notation we can write as v k comma k. This whole is multiplied by a j times d omega naught. And again, this j times d omega naught is d omega. So I can go back to my Eulerian description again. So this becomes integral over omega times d omega. And again, since I'm writing things in the current configuration, I can write my P star also in the Eulerian description. So the P star again will be a function of small x and t. There's a dot here plus times vk comma k. And this is our transport theorem. So I'll write that nicely. So d by dt, that's the material derivative of the extensive property or quantity Pij dot 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 as a function of time is the integral over the current volume omega of the quantity d by dt of P star, that is the corresponding intensive property Ij dot dot dot, which is Eulerian description, so small x and t, plus P star again times vk comma k times d omega. So this equation I'll box and I'll give it a label A. Now this quantity here is the material derivative of some property written in the Eulerian description. So I can use a material derivative in the Eulerian form and write this as d by dt of P star as a function of small x and t can be written as the sum of the local rate of change of P star, which is partial by partial t of P star, plus the convective rate of change of P star, which is written in the Eulerian description. So I substitute this into this equation And just for saving some space, this time I'll assume my property P is a second order tensor. So I don't have to write dot dot dot. So this becomes, so this part, as you can see here, this comes from the material derivative, and the remaining part was Vk comma k times P star. So now these two terms can be combined to get, and this form of the transport theorem will be tagged as A1. And in fact, in this term that we have here, we can apply the Gauss's theorem to convert the volume integral to an area integral, which results in this. And this form we will label as A2. So in this integral, if this is our volume omega, then the bounding surface is gamma, and d gamma is some infinitesimal surface element with a normal n hat. And usually this is the form of the transport theorem that is typically discussed in books and literature. So we'll call this as the Reynolds transport theorem, which sometimes is called just the transport theorem. So let's understand the terms in this transport theorem. So let's call these 1, 2, and 3. So the term 1 is the rate of change of the total quantity capital P as a function of time. And remember, this quantity capital P is the total P contained in a selected collection of material particles. And the second term here denotes a local rate of change of P star. So this basically denotes the amount of P which is created inside the volume. And finally, quantity 3, which is an integral over the bounding surface of the volume. So this denotes the amount of the quantity which is entering from the boundaries of the volume. And remember, these are rate terms, so we're talking about these things happening per unit time. Now, with this understanding of the transport theorem, let us put it into practice by deriving the conservation of mass equation. Let us define a few terms before we get started with this. So for this discussion, we'll be talking about the mass of a collection of particles, just like earlier. And this will be denoted by the symbol small m, denoting the mass of the particles. So let us say at time equal to 0, which corresponds to our reference configuration, these particles formed a volume omega naught. So collectively, their mass can be written as their mass at time t equal to 0 as the integral over the reference configuration volume omega naught times the density field, which is a function of capital X. So this is the Lagrangian description of the density field times d omega naught. And since this is the density of the particles in the reference configuration, this will be written as rho naught. So rho naught is that function that denotes the density of the particles at t equal to 0 in the reference configuration. And as time evolves, the same collection of particles will change their configuration. So let's say they now have this configuration, which we'll call the current configuration at some time t. So these particles form a volume omega this time, and their mass at time t will be given as an integral over this current volume omega of the density, which is written in the Eulerian description now, times d omega. So this rho as a function of small x and t is the Eulerian description. So if we specify some spatial point inside the current configuration, this function will give us the density of the particle sitting at that point in space at the time t at which we are considering the configuration. Now, of course, if I track a given particle r from the reference configuration to some current configuration later, the density of the particle r may change. So I can express my density function either using an Eulerian description, or I can substitute small x as a function of capital X in t to get the Lagrangian description, which is a function of capital X in t. And since this is a different function, I'll put a tilde here. And this function will explicitly tell us, if I specify, for example, the capital X for the material particle r here, I can track the density of that particle using this rho tilde function. Whereas my function rho is used to track the density of a spatial point small x with time. So different particles may be crossing at the same spatial point with time, but this function will tell us the density of the particle which is sitting at that spatial point for any given time. So these descriptions have different motives. So we have a rho, which we'll use to denote the Eulerian description of density. We have a rho tilde, which we will use to denote the Lagrangian description of density, and both are functions of time. And then we also have a rho naught, which is the density field at time equal to 0. So rho naught basically is rho tilde for capital X at t equal to 0. So I'll be using these symbols in our equations in the discussion that follows. So it is important that we understand the difference between these. So when talking about mass, let us see what the extensive and the intensive properties are. So in the transport theorem, we had a capital P, which for the conservation of mass will become the mass. So earlier I was talking about a quantity P for a collection of particles, and this time it is a mass for the collection of particles. And then our P star, which is the quantity per unit volume, will simply be mass per unit volume, and that will be the density field. So if I substitute these in the transport theorem, what I get is this. So dm by dt is an integral over the current configuration volume omega of the quantity rho dot plus the divergence of V times rho. And you can see that this is this form A of the transport theorem that we had written earlier. But this quantity dm by dt for a collection of material particles is 0, because the mass of a selected collection of material particles does not change with time. It stays the same. So this is m dot, and m dot is a 0 for a collection of material particles. So therefore, we can write that the integral that we have written here above is 0. And also our choice of the collection of particles was arbitrary. I did not tell you to choose a selected collection of particles. We had just chosen some collection of particles. And the collection of particles corresponds to the volume omega. So if the selection of particles was arbitrary, that means we could have chosen any sub-volume in my overall body. So this means that for this integral to be 0, for any omega, this means that this quantity has to be 0 identically. So we get this form of the equation, which is called the conservation of mass equation, also known as the continuity equation, which is written in the Eulerian description. and let's call this B. So you see that I don't explicitly write rho as a function of small x and t, but as I mentioned earlier that we'll be using the symbol without a tilde for Eulerian description. And for Lagrangian descriptions, we will use a tilde on the top. Now, just like in the transport theorem, we can also write the material derivative of rho in equation B using the local and the convective changes, which gives rise to this form for the conservation of mass or the continuity equation. So this we'll call B1. Since this equation is written over a volume, so what that means is for a given volume, if the density inside the volume is increasing, that is this del rho by del t, which denotes the density change at points inside the volume. So if the density inside the volume is increasing, that is only possible if some material is entering from the boundaries. So remember, we had written this using the Gauss's theorem as an integral over a bounding surface. So this term actually is called the mass flux. In fact, the mass flux is technically Vk times rho times Nk times d gamma. So V dot n is basically the velocity or the material that's entering normally from the boundaries, and it brings in some material with it or some mass with it. So this collectively is called a mass flux. And this term is the density increase inside the volume. So for a given volume, the only way the density can increase inside the volume is by some mass entering from the boundaries. Now let us take a special case of the mass conservation. So for incompressible fluids, such as water, which behaves like an incompressible fluid for a large range of pressures, the density of material particles does not change. So that's the meaning of incompressible, that the density of the different material particles does not change with time or stays constant. And please note that this idea of material particles here is very important, because for something to be incompressible, for a given material particle, its density should not change. Don't confuse it with the density change at a given point in space. Incompressibility requires that the density of a given material particle should not change. So in mathematical form, I can say that the material derivative of density has to be 0, which basically is rho dot is equal to 0. Now if I look at equation B, for incompressible fluids, rho dot is 0. So all we are left with is the divergence of velocity field times rho equal to 0. So if I divide by density on both sides, as I know that my density is always greater than or equal to 0, then the divergence of velocity is 0 for incompressible fluids. And such fluids or flows for which the density does not change are called incompressible, and such motion is called an isochoric motion. And we have seen this earlier as well in the previous lecture, where we showed that the divergence of velocity is 0 for isochoric motion. Now what is isochoric? Isochoric means constant volume. So if for a material particle whose mass is not changing with time, of course, and its volume also does not change with time, that basically means its density does not change with time. So we have seen the Eulerian form of the conservation of mass equation. Now we will see the Lagrangian form of the conservation of mass equation. So a couple of slides ago, we had written the mass of the collection of particles at t equal to 0 as the integral over the volume in the reference configuration for the density field rho naught as a function of capital X. And the mass for the same collection of particles at some later time was the integral over the volume in the current configuration for the density field rho as a function of small x and time. But since we're interested in the Lagrangian description, I'll write rho tilde as a function of capital X and t. In fact, this integral can be expressed as an integral over omega naught by simply substituting d omega as j times d omega naught. So we'll call this 1 and this as 2. And the conservation of mass requires that the mass of the same collection of particles does not change with time. So these two have to be the same. So this basically means that so if I move all the terms on one side, then what this means is that this integral is a 0. But again, by the same argument that our omega naught, or the collection of particles, was arbitrary, so this quantity inside the integral has to be identically 0. Or more explicitly, I can write rho tilde as a function of capital X and t times the Jacobian minus rho naught as a function of capital X is 0. And this is the Lagrangian form of the conservation of mass equation. So this we'll call C. In fact, more commonly, we write the material derivative of C, which results in d by dt of rho tilde, which is a function of capital X and t, times j equal to 0. Because the material derivative of rho naught, which is a function of capital X only, is a 0 because it's not a function of time. And this form we'll call C1. So with this, we have finally derived the Lagrangian form of the conservation of mass, or the continuity equation as well. So as a summary, today we derived and wrote the form for the transport, or the Reynolds transport theorem, which forms the basis of writing conservation laws. And then we applied this to the conservation of mass to get the Eulerian as well as the Lagrangian forms of the conservation of mass, or the continuity equation. In the next lecture, we will talk about the conservation of momentum, both the linear and the angular momentum. So before we close, just a point on the mathematics. In the beginning, when talking about the derivation of the transport theorem, we had written the quantity P as an integral over omega for P star times d omega. And then what we did was, since we wanted to write the material derivative of P with respect to time, we converted this to a sum or an integral over the reference configuration, because then d omega naught is not a function of time. So we could move the derivative d by dt inside the integral. But that is not really necessary, because what we can do is we can keep this on d omega. So this still stays P star. And then what we write this as? We write this as the integral of d by dt of P star times d omega plus an integral over omega of P star times d by dt of d omega. Because in this case, our omega is also changing with time. And if you recall from the last lecture that this material derivative of the volume element was expressed as the Jacobian times the divergence of velocity times d omega naught. And this j times d omega naught is basically d omega. So I can remove this j and I can call this d omega. So this simplifies to integral over omega of p star dot plus p star times the divergence of the velocity times d omega. And this is exactly what we had gotten. But usually it's always safe to move to a configuration where things do not change with time so that we can move the derivatives inside. But if you know how the volumes are changing, you can use the material derivative of infinitesimal volumes to get the same expression. So with this, we close this lecture. Thank you very much, and I will see you in the next lecture.